Good afternoon. My name is Narasimhan Swaminathan, a faculty here in the Department of Mechanical Engineering at IIT Madras, and welcome to this phase of QEEE program where we have this session on machine design on machine elements. For this particular course, I'm planning to teach a couple of topics related to that. So as you might have seen in the course material, if at all you had a chance to log in and take a look at what has been posted there, you will find a couple of different PDF documents, and each of them addresses two different topics, but mainly the content that I'm going to deliver is related to failure theories. So of course, design of machine elements, how does it relate to failure theory? So this is the fundamental thing that you need to know in order to design any machine element, whether it be a shaft or a gear or a spring or any sort of mechanical engineering component that you are going to be dealing with in your day-to-day activities. If you want to have some sort of a back of the envelope calculation so that you can understand whether the loads that particular component is being subjected to, whether for that particular kind of loading this component is going to fail or not. When I say fail, it means not necessarily break, but it could mean say local yielding, where somewhere it could have reached some sort of a plastic deformation, permanent plastic deformation, because of which this particular component is not useful to us anymore. So anything that is associated with a phenomena because of which you are not able to use that element, machine element any longer, we will term as failure. So failure theories, understanding failure theories forms a very important component of designing any machine element, and this forms the important component of the design of machine elements course in general in any mechanical engineering curriculum. So that is the reason I am planning to teach this part of the course which is related to design of machine elements. So these are the various topics that I want to cover. So some introduction as to why we want to understand these things, and then whenever we are talking about failure, what are we dealing with? We are dealing with the stresses in the material reaching some critical value, or some combination of stresses in the material reaching some critical value, and after which it basically fails. So so this is an example of a brittle failure. As you can see, a chalk piece is a brittle material. So what we want to do is we want to understand how we can quantify the failure so that we can do some very simple calculations, not necessarily on a computer, but probably at the back of the envelope calculations as they are called, so that you can find out the geometry that you can have for this particular component so that it does not fail for a given loading. Or if you are stuck with a given geometry, you will be able to determine what is the maximum load that this particular machine element can basically withstand. These are the kind of things that we need to know. For that, the most essential understanding has to come from the basics of mechanics of materials, which you would have studied in your third semester, and you need to know some concepts from a little bit advanced continuum mechanics, solid mechanics as they call it, something related to stress tensor, principal stresses and variance. That is what will be covered next. And then we will go into how you can divide the stress into two different categories, and how one particular category plays a very important role in a very famous, very important failure criteria, which is the von Mises failure criterion for ductile materials. And then we will talk about some basic mechanisms which basically govern failure. Why do materials fail? What is the fundamental atomic level mechanisms that is going to cause the material to fail? And then of course we will talk about a few failure mechanisms or failure theories associated with brittle materials. So essentially we want to do the following. Failure theories will be categorized into three parts. Firstly, I will talk a little bit about stress principles, then ductile failure in materials, and then brittle failure in materials. So these are the various things that we want to talk about. Basically, we want to be able to give proper quantification to the word failure. That is the essential goal of this session, and how we do that. So then we will talk a little bit about factor of safety. You might have heard this term several times, so we will go over it pretty quickly, and then talk briefly about what it means to say stress concentration whenever you have some sort of geometric singularity in a number. For example, if you have a bar and it is loaded by a load P, then in general the stress at any given cross section, if the cross section is A, then the stress is P by A. But at the same time, if you have the same bar, but however in this bar you have provided some sort of a hole, say for example you wanted to put some screw there or something like that. Now if you subject it to the same P, then the stresses in the vicinity of this hole are going to be very high. Okay, the stress distributions are going to be slightly different. Now to account for that stress increase because of the presence of such singularities, every time you cannot do some complicated computational analysis in order to figure out what the maximum stress there is. You want to find out whether that particular spot is failing or not. Every time you cannot do some complicated analysis. So we have some back of the envelope or some intuitive way, based on, of course, intuitive in the sense it doesn't come from the air. It basically comes from theories of elasticity, by which you are able to predict by what amount will the stress be higher here when compared to the stresses that are induced in a member without this geometric singularity. So that brings in the idea of what is referred to as stress concentration. So this is something that we will study, and then we will probably conclude the session with this particular topic. So let's get started. So whenever we are going to design machine elements, what are we basically looking for? We are looking for the fact that these machine elements should not fail in service. Okay, the word failure again is quite general. It could mean anything from breaking to actually undergoing some small minor plastic deformation somewhere, because of which it becomes completely useless. So in different instances, failure can mean different things. So we need to know a priori and define failure for our convenience. Okay, that is the first thing. So these machine components are subjected to very complicated loadings in general, and these loadings cause stresses, and whenever some combination of these stresses reach a critical value, the material is assumed to have failed. So the main idea is to be able to decide a geometry for the component, a material for the component, so that it does not fail under given loading, or if you are stuck with a specific loading, you should be able to find out what the best geometry the particular component can have so that it does not fail. So either of these two problems can be handled by some of the theories that we are going to talk about. The topics or the kind of loads that are generally important to us are of two types of loads are generally important to us whenever we do failure analysis. We have to know whether the load is static or whether the load is dynamic. So when we say static, what does it mean? Very simple, right? The word itself has the meaning in it. So if there is a bar, so I like this bar example. I will usually use this to give you some simple idea as to what I am trying to say. So you have the load P here. This load P is not varying with time. Okay, so it is a static problem. Okay, me standing on this, if I stand on this table, and forever if I stand on this table and I want to find out when this particular table is going to fail because of me standing there, that is a static problem. Okay. Now if I have another bar, but now the load P is not static, but it is varying with time. This is cos omega t. Okay, it's varying with time t, so it is varying with time sinusoidal. Okay, something like this. So in this case, this is time and this is the load. Okay, P is a function of time. So in this case, the load is not constant, but it is varying. So these two problems have to be dealt with in different manner, because the mechanics or the microstructural level details which govern the failure of the particular material is different when the load is varying with time, as opposed to when the load is actually stationary or fixed. So we need to address these two issues. So this is what I will talk about first. Later on, in the second part of the last The last two sessions will probably be dealing with fatigue failure. Okay, dynamic loading leads to fatigue failure. All that I have been saying so far is I have been basically introducing the subject and telling you why failure theories are important, and I've been telling that there are two different types of loadings that essentially your machine elements are subjected to. One is called static loading, other is called dynamic loading. In static loading, the load is actually fixed in time, whereas in dynamic loading, which causes fatigue failure, this causes static failure. Okay, static failure of the component. Here fatigue failure of the component is caused because of time varying load. It need not necessarily be sinusoidal or cosine or something like that. An aeroplane which is landing, it's subjected to all sorts of arbitrary loads, and the loading will be something like, on the landing gear, it will be like completely arbitrary, it will look like noise. Okay, so basic idea is to understand that the load varies with time, and you need to account for the fact that the microstructural mechanisms which cause failure under time varying loads is different from what it causes when the load is static. So these are the kinds of stuff that things that we are going to deal with. So the first primary thing that we need to know is stress. So you all have learnt stress in your mechanics of materials. What is stress? Stress is basically the resistance that the body offers to deformation. Okay, that is a very important definition. Okay, the resistance offered by the body to deformation is called stress. So if you have a bar, okay, a bar like this, and if you uniformly heat it, okay, so you increase the temperature by delta T. So initially the length is L. After you heat it, the length increases by some amount. Okay, if the coefficient of thermal expansion is alpha, then what is the change in L? Alpha delta T multiplied by L will be the change in length that is associated with this bar, right? Now you need to ask the question, the body is subjected to a change in its length, but does that mean that it is subjected to stress? The answer is no, right? It is free to expand. There is nothing resisting the body's deformation. So essentially no stresses will be induced if you simply heat the bar. It's a very important concept. However, if I do something else, if I now fix the other end of the bar also and now heat it, the body does not change its length at all. Okay, because I am fixing it on the other end and heating it delta L. Okay, assuming that this is just a bar, that it is not going to deform like a beam or anything like that. In this case, the bar is trying to expand, but I am preventing the deformation by fixing the other end, because of which some sort of compressive stresses get induced. So only if the body is going to resist the deformation will you have stresses getting induced. So in mechanics of materials, whatever you studied was generally uniaxial state of stress. Of course, you must have looked at some sort of plane stress, plane strain approximations, but in general they all are only dealing with one stress component. Either you found out what is the normal stress, bending stress in a beam, or you found out shear stresses during torsion and things like that. But stress is a slightly more complicated quantity, and it is referred to what is known as the stress tensor. So as you can see on the slide here, we have a body, so we have an arbitrary body, now not necessarily a beam or anything like that, any arbitrary body, and this body is fixed on at different points, and at other points it is being subjected to different kinds of loads. So I might have uniformly distributed load here, I might have some point load at this particular point and some moment here. Okay, now because of all these loads that is acting on it, and because of the fact that I am kind of resisting the motion of certain points, the body will get some sort of a stress distributed in it. Okay, there will be a stress distribution in it, and this stress distribution can be pretty complicated. And in general, if you take any infinitesimal volume element, like what you can see on the slide right here, there is a small volume element, and that particular volume element is given a particular position coordinate r with respect to the coordinate system that I have marked there, x, y, z, okay, and you can see that that particular infinitesimal volume element has different stresses acting on it, right. So the stress is generally represented by either the Greek letter alpha for normal stress. So if there is a plane and if there is a stress component that is acting normal to it, that means the stress component and the normal to the plane are both in the same direction, then it is a normal stress. Whereas if the stress direction and the normal to the plane are in orthogonal directions, then it is basically the shear component of stress. Okay, so we have two suffixes which represent the direction. One represents the direction in which the stress is acting, other represents the normal of the plane on which the stress is specifically acting. So that is the convention that is generally used. So I have just specified here. So the alphas basically talk about the plane represented by the normal, and beta represents the direction in which the stress is acting. So if I say sigma 1, 2, what that essentially means is, so 1 is basically the plane. So this is one direction. So 1 means say the x direction, and 2 means it is the y direction. So I should not use the symbol sigma here, I should use the symbol tau to represent shear stress. So this will be tau 1, 2. Okay. Actually it doesn't matter at this stage whether I use alpha beta or beta alpha, simply because the stress tensor tau 1, 2 and tau 2, 1 are both same for the purposes of this class. It need not be the same at all in all conditions. For the purposes of this class, tau 1, 2 is equal to tau 2, 1. You must have also studied a proof for this in your mechanics of. So the stress is actually the physical quantity stress, which represents the resistance of the body to deformation, is basically a complicated mathematical entity called tensor, and this particular entity has in general 9 components. So they are sigma 1, 1, tau 1, 2, tau 1, 3, tau 1, 2, sigma 2, 2, tau 2, 3, tau 1, 3, tau 3, 2 and sigma 3, 3. So tau 3, 2 and tau 2, 3 are both basically the same. So I can just use tau. So this is the stress tensor. At every given point in the material, remember the point is specified by a coordinate system, there is this matrix taking place at every given point. Okay, there are 9 different values of stresses, of which 6 are independent, because this is equal, these are all equal, this and this are equal, this and this are equal, so which 6 are independent. So we have 6 different components of stresses, and that is at every point in the number. Okay, now it is very difficult for us to deal with 9 different numbers whenever we are dealing with failure theories. We usually like to have one single number, and that is basically the that is where the failure theories basically help us. So stress state at a particular point is written as a matrix in general, and it consists of 6 independent components. I'm just recapping what I've been telling so far. It has 3 normal and 3 shear components. One important thing for us to remember is this stress tensor, this physical quantity that we have, is also needs a specific coordinate system to write. Okay, it is written in a specific coordinate system. For example, you can have some coordinate system like this. In this coordinate system, the stress tensor at point P is this. Okay, now I can take any other coordinate system. So let me rotate this coordinate system arbitrarily and I get something else. Say for example, so this dashed line becomes my y dash, this is my z dash, this is my x dash. Now I have rotated the coordinate system, but still the loading that is there on the body, the boundary conditions are all fixed. I have just changed my the coordinate system. Okay, what will happen? These numbers will change, but they still represent the same physical resistance the body has. So what I was saying is this physical quantity called stress tensor is occurring at every point in the body that is being loaded, and when you change the coordinate system, each of these numbers change to something else. However, you need to understand it is the same physical quantity that we are talking about. So to give you a better example, let us take, say, it is something like this. A useful example is to look at the velocity vector. So velocity vector is much more easier to comprehend than stress tensor. So let's take a coordinate system xy and let's talk about a vector v, which is nothing but the velocity. It has two components, vx and vy. So this entire vector can be written as vx times I hat plus vy times j hat, where you know the I hat and j hat are essentially the unit vectors along the x and the y direction. Now this is the velocity vector. It's a physical quantity which requires a specific coordinate system to represent. Now let us rotate this coordinate system a little bit. So let this be x dash and let this be y dash. When I do that, the velocity vector in the new coordinate system x dash and y dash becomes different, right? So you have v x dash, say I hat dash plus v y dash j hat dash. Okay, both are the same velocity vectors except that they are written in different coordinate systems. Now what is changing? The components are changing. Okay, components are changing, but there is something that is common to both. What is it? This, if you find the magnitude of this velocity in both the cases, it will essentially be the same, right? You can vx square plus vy square will be equal to square root of vx dash square plus vy dash square. So in a similar spirit, the stress tensor is also a physical quantity, except that instead of one suffix you need two different suffixes in order to represent it, and depending on the coordinate system, as you change the coordinate, rotate the coordinate system, you will find that the components of the stress tensor actually change. They will change, but something about the stress tensor will essentially not change. Okay, it is the same physical entity that we are talking about. So one of the things that we need to understand comes from the understanding that stress is this physical quantity called stress requires a coordinate system, and the components will change when you change the coordinate system, and there is one specific coordinate system which when you choose, it so happens that your shear stresses completely vanish. There is a special coordinate system if you choose some x triple prime, y triple prime and z triple prime, or double prime. If you choose, the stress tensor will reduce to this. Basically all the shear components will completely go away. That particular coordinate system is called as the principal coordinate system. The set of these three stresses is called as the principal stress. Okay, generally we write it as sigma 1, sigma 2 and sigma 3. Remember, all you are doing is rotating the coordinate system. You have not lost any information with regards to the nature of stress that is getting induced, and this is also at one specific point in the arbitrary loaded member. Like this you can do for every point that is having a stress tensor, and you can find out what the values of the principal stresses are. So now we have actually made our problem slightly easier. So whenever we are talking about failure, we want to compare these stresses to something else, so as to say something is failing or something is not failing. Now previously we had 6 different components to probably compare, which we never knew how to do, but now we are actually reducing it to just 3 components. Now still this is difficult, so we want to reduce it to just one component so that it makes our life even more easier, and it needs to be done with some physics in mind. So what is that? We will talk about those things as we are making progress. So these are called as the principal stresses. and we need to use these stresses in the some of the failure theories that we are going to be talking about. Now I want to tell you how we find out these principal stresses. So it's just impossible for you to rotate the coordinate system arbitrarily by infinitesimal amounts and find out one particular coordinate system for which these shear stresses vanish. There is a way, but that is going to take one lifetime to basically figure out, or even then you cannot figure it out. So I will tell you some other methodology by which you can find out these principal stresses. Okay. So first we need to understand a concept referred to as, understand a concept called as traction. So now let us take again an arbitrary loaded member and take a particular point P. Okay. Then it's arbitrarily loaded, there's arbitrary stresses on the material. Now what we are going to do is, we are going to pass a section through this P and isolate the left hand side off. Let me okay, the point P is here. Okay, this is a point P. At this point P, there was some stress induced because of the arbitrary loading. Okay, I am passing a plane through that. That particular plane has normal n, and the components of n are given by, say, n1 I plus n2 j plus n3 k. Okay, these are the components of this normal. Now at this particular point P, there is some stress tensor. Okay, that means at this particular point B, we have these components: sigma 11, tau 12, tau 13, tau 12, sigma 22, tau 23, tau 13, tau 23, and sigma. Okay. Now the component, the vector called stress is nothing but, I'm going to write it like this, If you do an operation like this, okay, if you multiply the stress tensor with the components of the normal of this particular plane, what you are going to get is, you are going to get T1 will be equal to sigma 11 this will be T1 and it is pointing in the I direction. T2 will be tau 12 times N1, sigma 22 times N2, tau 23 times N3 pointing in the J direction, and tau 13 will be similarly pointing in the K direction. Okay, so that is, this set of components are nothing but the components of what is referred to as the traction vector. It's called as traction. It should be clear. So this is the stress tensor. Okay, at this particular point, I have passed a plane through it. I'll tell you why this is important. Okay, just follow what I am saying. You will find out why it is important. Okay, this is the stress tensor. This is the normal. This is the plane through which is passing through point P, and there is a normal for this plane. The plane is represented by the normal. There is nothing more important to a plane than its normal, right? It has components n1, n2, and n3. These are the direction cosines of the normal, so to speak. So it follows the rule that, square root of n1 square plus n2 square plus n3 square is equal to 1. So they are the direction cosines, and if you multiply, if you do this operation, you find a vector. T1, T2 and T3 are components of the vector, and these are called as the traction vectors. traction vector. For any arbitrary plane that is passing through this particular point P, the traction vector is oriented in some direction. Traction vector is oriented in some direction for this particular. Now tell me what would happen as I made this traction vector coincide with n. Just think about it. You can't tell me, I can't hear you now, but I'll give you maybe a minute to think. So I'm actually changing. What I'm doing is I am basically asking you the question, what happens when this traction vector and this n are both coinciding? The directions are coinciding. So when these directions are coinciding, what will happen is that the shear stresses basically vanish. The only thing that remains will be the normal stress along this particular normal. Okay, along this particular normal to the plane. Okay. Now when the shear stresses vanishes in this plane, what type of stress is it? It is a principal stress for this particular plane. Now we ask the question, how many such planes are there? How many such planes are there? How many such principal planes can we basically find? So in order to do that, we basically try to enforce the mathematical constraint that I just spoke about. So what did I say? I said that the traction vector and the normal must both be in the same direction. That means T must be equal to some scalar multiple of the normal vector. If I find some such combination of lambda and normal, normal means what? The plane. If I find out some such combination of lambda and n, I am essentially finding out the principal stresses for that plane, because the shear stresses will be absent if this condition is satisfied, right? So we do that. So let, in any arbitrary coordinate system, let P have a stress sigma 11, tau 12, tau 13, tau 12, sigma 22, tau 23, tau 13, tau 23 and sigma 33 times the various components of n, because that is what is the definition of T. T is nothing but the stress tensor times the various components of the normal. This must be equal to lambda times n1, n2, n3. So what does this mean? This means if I do the little bit of math that I have to do here, I get something like this: sigma 11 minus lambda tau 12, tau 13, tau 12, this must be equal to 0, right? What I have done is I have just brought this to the other side. You will get it in the form of this particular expression right here. So you want to find the corresponding values of n1, n2, n3, okay, but on the right hand side you have zeros. So how will you get non-trivial solutions for this case? How will you get non-trivial values of n1, n2, n3? The only way by which you can get it is by making the determinant of this go to 0. Okay, those values of lambda for which the determinant of this matrix goes to 0 will give you the set of lambdas for which this gives you non-trivial solution. So what I'm going to do is I'm going to do this: sigma 11 minus lambda must be 0. So when I enforce this constraint, I'm not going to do the entire math, it becomes a little bit messy here, but when I enforce this constraint, when I do this, okay, what is the goal here? The goal is to find the set of n1, n2, n3s, that is that particular plane, no? I'm passing a plane through this, no? The set of normals, the set of the direction cosines for this particular normals I want to find such that both the normal and the traction vector are in the same direction. Because when that is the case, there is no shear stress in this plane, because all that stress is going in the same direction as the normal. Okay, so that is the goal. When I did that, when I enforced it mathematically, it is telling me that if you want to find out these numbers, you have to make sure that this determinant goes to 0. That means the value of lambda I have to find for which this determinant goes to 0. So this, when I do this determinant, when I try to enforce the determinant going to 0, I get basically a cubic equation in lambda. Okay, I get a cubic equation in lambda, and that should be on slide number 9. You can take a look at it on slide number 9. Somebody, if they're there in your college, you can ask them to change to the slide number 9. You will see equation number 9, which is basically the equation that I have written on the board also. It's a cubic equation in lambda for which you can solve for lambda. Okay, you can find the values of lambda, right? If you have a computer, you can use some computational technique, or if it is a simple structure, this will nicely reduce, and you can actually find the values of lambda analytically. We will do a simple problem. Now there will be 3 values of lambda that you will find. So lambda 1, lambda 2, lambda 3, which will satisfy this equation. And these 3 lambdas are the principal stresses of this stress tensor. They will be the principal stresses. Okay, lambda 1, lambda 2, lambda 3, which are the solutions to this equation called as a characteristic equation, which will basically give you the principal stresses. This is the way to find the principal stresses, not by infinitesimally rotating the coordinate system until you end up with a case where all the shear stresses are 0. You cannot do that. Okay, this is the right mathematical way to do. Now, what are these I1s, I2s and I3s? Now, this is a very important thing. So, when we talked about the vector, when there were different coordinate systems, when we rotated the coordinate system, there was one thing about the vector which did not change. What was it? The velocity, the magnitude, right? The speed did not change. In a similar spirit, for this physical quantity, which requires 2 directions and 6 different numbers to specify its state at a given point, you have 3 different numbers which will not change no matter how you rotate the coordinate system. For velocity, there was one invariant. The speed was invariant no matter how you rotated the coordinate system, right? For the stress tensor, there are 3 invariants. I1, I2 and I3 are the 3 invariants of the stress tensor. They will not change no matter how you rotate the coordinate system. What that essentially means is, if I have a coordinate system, say x, y, z, okay, and I write the stress tensor for this. Now I write the same, at the same point, I write the stress tensor using a different coordinate system. Now again, another one. What it means is, for each of these stress tensors, each of them having different numbers. They have different numbers here. Okay, sigma 11, this will be sigma xx, tau xy and so on. This will be sigma x dash, tau x dash, y dash and so on. This will be sigma x double dash, tau x double dash, y double dash and so on. For each, the numbers are all different, but when I write down the characteristic equation, they will all have the same values for I1, I2 and I3. And what are these I1, I2 and I3s? I1 will nothing but be the sum of the 3 diagonal components, the sum of the 3 diagonal components, so sigma xx plus sigma yy plus sigma zz. So it will be related to the hydrostatic stress, 3 times the hydrostatic stress, where hydrostatic stress is nothing but sigma xx plus sigma yy plus sigma zz divided by 3, or sigma x dash, sigma y dash plus sigma z dash is z dash divided by 3 or the corresponding values of x double dash, y double dash and z double dash. Okay, that will be the hydrostatic stress. The third invariant will be the determinant of the stress tensors. They will also not change when I rotate the coordinate system. The second invariant will be the negative of the sum of the principal minors. Take a look at slide number 8. So I have clearly defined what this sum of the principal minors are. It's nothing but, you hold this fixed, you determine the determinant of this set of component, plus hold this fixed, determine the determinant of the minor there, and that's what minor means. So let me not explain what minor means. So negative of the sum of the minors will essentially be the second invariant. These three numbers don't change no matter how you rotate the coordinate system. So this is very important. So whenever you want to find out the principal stresses, remember you have to solve this characteristic equation first, because that is what is going to give you three different values for lambda, which are essentially the principal stresses. So whenever you want to write I1, I2 and I3, you don't necessarily have to go through this sigma 1 1 minus lambda, sigma 2 2 minus lambda, take the determinant, do all such things. It becomes very easy if you know that I1 is sigma x, the sum of the diagonal components, I2 is negative of the sum of the principal minors, and I3 is nothing but the determinant. So you can easily find out what the characteristic equation is, and once you know what the characteristic equation is, you can find out the principal stresses. So now you know how to find out the principal. So just to illustrate here, I have a problem. Okay, let's do the problem now. So we have the stress tensor is 57, 0, 24. You are asked to find the principal stresses. Okay, you want to find the principal stresses here. Okay. So first step is to write down the characteristic equation. So the characteristic equation will be lambda cube minus I1. What is I1? This plus this plus this. What will it be? So then the negative of the sum of the invariants, whatever it is. So you have to close this, take this times this. So 50 into 43. So I will just write down here. Okay. Plus the determinant. You have to write down this particular equation and solve it. Okay. But I told you that writing it like this and finding out lambda can be easy sometimes. But in this case, it actually complicates things. If you write it down the other way, from the more fundamental way, you will see that it reduces to the required characteristic equation in a much more simpler manner. So you have to be careful. So what do? Put minus lambda everywhere and then perform the operation. Determinant of this must be equal to 0. What do you get? 57 minus lambda times right. So now you can see that you can pull out this 50 minus lambda and you get so this was much more simple. This is much more simpler than actually writing the characteristic equation if you know the invariance. So in some circumstances this is much more useful. So you just have to see if your numbers are turning up too large, you just have to try to do the other way to make sure that you get your answer reasonably quickly. So now from this you can easily tell what the what one principal stress is, right? 50 minus lambda multiplied by this quadratic equation is equal to 0, which essentially means lambda must be equal to, right? That is one principal stress. one solution for the characteristic equation. This is a quadratic equation in lambda, and you can use your minus b plus or minus b square minus 4c, but let me tell you, this will also boil down to a very simple expression. It does lambda square minus 100 lambda minus 1875 is what you will get here. You're right. Yeah. So this equation is what reduces to this, and this, you can easily find the roots of this also, which is lambda minus 50, lambda minus 25 times lambda minus 75 is equal to 0. So the principal stresses for this case are 25, 50 and 75. You can try it out later on if you want to. What I want to highlight is this. I know you can do this math very easily, so let's not spend time on that. Okay. What I wanted to highlight is, you see 50 is a eigenvalue, right? When I should not use the word eigenvalue, it's a principal stress. 50 is a principal stress. If you look at this particular the tensor that I gave you, sigma 11, sigma 12, sigma 21, sigma 23, sigma 23. On the second plane, okay, other than sigma 22, all the other shear stresses that can act are basically 0. So 50 has to be a principal stress. Whereas for the other two planes, 24 is there, you have the shear component. So they are not the, these two will not be the principal stresses. You have to find the principal stresses will be 25 and 75 respectively. Okay. So in this way, you can find out the principal stresses of a given stress tensor, number one. Number two, the invariants, not only is it important to write the characteristic equation, the invariants play a very important role in failure theories also. So let's just continue with the same problem that we have been looking at. So this was the stress tensor that was given to you, and we wanted to find out the principal stresses. So what I'm saying is, sometimes by just looking at the stress tensor, you will be able to say, identify one or two principal stresses. So in this case, it so happens that this is 50 is a principal stress simply because the components, the shear components in that particular plane, this is the two plane, in the two direction it has some value, but 1, 2, 2, 3, the shear stresses, the shear stresses that may act in the two plane are all 0. So basically 50 has to be a principal stress. And the other principal stress are 25 and 75, which you will have to find out using the procedure that I just discussed. So as a recap of what we have been trying to do is, we have to find out when we have to find out the principal stress, we can adopt two strategies. One is simply put minus lambda to the diagonal components, take the determinant equal to 0 and find out solve that cubic equation. Or you can simply blindly write down the characteristic equation, where each of these things are invariants, so you can easily calculate it from the stress tensor and write it down and then solve this equation. Both are basically equivalent methods. It's just one of the methods might save you a little bit of time in trying to find this out. Now we find the principal stresses. So the principal stress, what does it give you? It tells you the value of the normal stress. That's it. So if this was the body and this was P, it is telling you the component of stress in this direction. It is telling you that scalar multiplier. So if this sigma times n1, n2, n3, this was the traction, was equal to a scalar multiple times n. This lambda or the scalar multiplier is basically that the three principal stresses, telling you that there are three such principal values, three such values for which the traction and the normal component can basically coincide. So those three components, one, but we never still found out in what direction is that plane present. That means what are the direction cosines of the plane? We still need to find that out, right? Only then do we know what is the coordinate system to which we need to rotate our current coordinate system, so that at that particular point all the stresses are only normal. That means all the shear stresses are zero, or we have obtained the principal coordinate system. So how do we find that out? So let us take the current example that we have. So it is 57, 0, 24, 0, 50, 0. Okay. So the thing is, the equation that we have to solve is, the principal stresses are 25, 50 and 75. I'm going to do it for this 25 case currently. So what happened? So first, this was the equation that we had to solve, right? Minus lambda times n1, n2, n3. Remember, n1, n2, n3 are the direction cosines of the normal corresponding to the principal value, or the corresponding to the value lambda. Okay, this lambda can be either 25, 50 or 75. For each of these three principal values or principal stresses, you will find three such normal vectors. That means there can be a vector like this, there can be a vector like this, and there can be another vector going through the board which is essentially perpendicular to the other two. The normals will be perpendicular to the other two. So one of the some properties of this normal which we all know is that, firstly, the normal corresponding to this, the normal corresponding to this, these two will be perpendicular. They will be mutually orthogonal. Okay, the three will be mutually perpendicular to each other. They form a coordinate system basically. Then each of these components satisfy the criteria n1 square plus n2 square plus n3 square is equal to 1, because each of them are direction cosines. Okay, they are direction cosines, so they have their unit value. Now what I am going to do is, I am first going to demonstrate how you find out this n1, n2, n3, the direction cosines for this corresponding eigenvalue, that is 25, this corresponding principal stress 25, and you can do for the rest. So what we do is, first we substitute this right there, so it becomes 57 minus 25, so you have 32, 0, 24, 0, 25, 0, 24, 0, 25, 18. 43 minus 25 will be 18 times so like what you do in linear equations, you can write down this, right? It becomes 32 times n1 plus 24 times n3 is equal to 0, 25 times n2 is 0, 24 times n1 plus 18 times n3 is 0. Now you can make a very good observation. Firstly, it says that n2 is 0, right? 25 times n2 is 0. That means for this particular eigenvector, n2 is 0. That means it has no component along the two direction. Okay, and this was true because 50 was already an eigenvector. That means the second coordinate is x, y. So one is x, two is y, means y is already pointing in the direction of the principal coordinate system. Okay, so n2 is 0. Then these two, if you take 32 n1 plus 24 n3 is equal to 0, if you take both of these, give you the following. So 8 3s are 4s are 4 n1 is equal to minus 3 n2. From the other equation also, you will get exactly the same relationship. You will get 4 n1 is equal to minus 3 n2. So what this means is, you may assume So let n1 be arbitrarily taken as 1, because n1 is just the direction cosine, right? You can always find it out. So n1 is 1, then if n1 is 1, then n2 has to be equal to minus 4 by 3, that's it, minus 4 by 3. Okay, you found n1 to be 1, you just guessed. This is the relationship n1 has to have with n2, that's all. That is the only condition that you can have between n1 and n2 from these two equations. n1, if you assume arbitrarily as 1, n2 can be taken to be minus 4 by 3 because it has to satisfy this relationship. But you also know that it has to satisfy the following relationship, right? That is n1 square plus, so all these things, n1 square plus n2 square plus n3 square is equal to 1. This is equal to 0. You know that is equal to 0, right? So what you can do is you can normalize each of these things so that sum of n1 square plus n2 square will be equal to, you know how to normalize the components of a vector, right? So in a similar manner you say that n1 normalized will be equal to 1 divided by square root of 1 plus 16 by 9, and n2 normalized will be equal to minus 4 by 3 divided by square root of 1 plus 16 by divide each component by the magnitude of that vector, and you will get n1 hat and n2 hat, which will give you the normals in which the principal coordinate system for the principal value of 25 points. Okay, and that will happen to be the answers are there in that slide. It will be 0.6, 0 and minus 0.8 for the eigenvalue 25. You should try it out. So once you try it out, you will get a little bit more comfortable with it. So with that, what do we know now? So we know that given a tensor, there are something called invariants which will never change how the coordinate system changes. There are three different invariants, first, second and third. First is nothing but the sum of the diagonal components. The second is basically the negative of the sum of the invariants, and the third one is the determinant of the stress tensor. Okay, we know how to find these invariants. Another important concept as far as stresses are concerned is the division of the stress tensor into two components, which is the hydrostatic stress and the deviatory stress. Okay, this is very important because whenever certain materials are exposed to stresses, the component of stress which does this is not going to cause the material to fail, whereas the component of the material which induces this deviatory part causes the material to fail or yield. So I'll tell you what this is. So hydrostatic means you know what it is. So it's nothing but sigma 11 plus sigma 22 plus sigma 33 divided by 3. Okay. So from the total stress tensor, if you subtract out the hydrostatic component, you will get the component is called as a deviatory component. So you can take a look at this in slide number 11. Okay. In slide number 11, I have written down the hydrostatic component. So hydrostatic component is nothing but I1 by 3, right? I1 is nothing but sum of the diagonal elements. So I1 by 3 will be the, you can write down the hydrostatic component in the manner that I have written. If that is the case, you can write down the deviatory component by subtracting each component in this manner. So if this is minus sigma xx plus sigma yy plus sigma zz by 3, the same thing here and the same thing here with all the elements 0 will essentially be the hydrostatic stress. This will be the hydrostatic component of the stress tensor. This will be the total stress tensor. If you subtract the two, you will get what is called as the deviatory component of the stress tensor, which is basically there on your slide, equation number 13. Okay. Now it can be shown that for any arbitrary point which is loaded in a specific way, only the deviatory component causes a change in shape. Okay. So let us illustrate that with a very simple example. So why is this deviatory and hydrostatic differentiation important for us? So it is definitely important, but Let me tell you how. So if you take a small infinitesimal element which is subjected to say uniaxial compression, sigma 1, sigma 1. If I want to split this into the hydrostatic part and the deviatoric part, it's the same element, I am going to add up the stresses. So sigma 1, so as far as this infinitesimal cube is concerned, the shear stresses are all 0 and the normal stresses only one is there, that is sigma 1 is there, sigma 2 and sigma 3 is 0. So the hydrostatic stress will nothing but be minus sigma 1 plus 0 plus 0 by 3, minus because it is compressive. So the hydrostatic component is nothing but minus sigma 1 by 3. So we are going to have minus sigma 1 by 3 minus sigma 1 by 3 and going into the board, compressing the cube also minus sigma 1 by 3. So that will be the hydrostatic component, right? Okay. Now what will be there here? Here you will have minus sigma 1 minus sigma 1 by 3, and that will be equal to minus sigma 1 plus sigma 1 by 3, or 3 minus 2 sigma 1 by 3. So you will have, so let me just indicate the fact that it is compression by the arrows and leave this number positive, okay, just for being clear. So basically what I have done is, I put a minus sign here, but it is not needed. The fact that it is compressive is indicated by the arrow. Okay, I am just writing the magnitude for all the cases. So same thing here. The deviatory component, one particular deviatory component is minus 2 sigma 1 by 3. The other one will be 0 minus of minus sigma 1 by 3, which is equal to sigma 1 by 3. There will be tensile. Okay. Similarly, in the z direction or z direction also, out of the board also, it will be coming out. So imagine this cube. Okay, this cube, when it is subjected to uniaxial compression, there is a component of the stress tensor which is causing it to compress in in all the three directions. That means this is only going to result in change of the volume. That means a cube remains a cube, whereas the volume alone changes, right? It just becomes a smaller cube when it is subjected to only the hydrostatic component of the stress. But here, what is happening? The top and the bottom faces are being flattened out, whereas the central, whereas the side ones, these and these are being pulled apart. That means a cube is converted into a cuboid. There is going to be a change of shape, right? So in all the stress tensor, the total stress tensor at a particular point, the hydrostatic stress contributes to volume change, whereas the deviatoric stress contributes to shape change. So now we come into the various theories of ductile failure, because this is what is important to us. Before that, I'd like to point out that just like how there are invariants for the stress tensor, you can have invariants for the deviatory component of the stress tensor. So the deviatory component of the stress tensor is equation 13 on slide number 11. Okay, you can write down the various invariants in a similar manner. The first invariant, what will be the first invariant? Be 0, right? Because you are summing of the diagonal components. So if you sum it, you will get 0. But the second and the third invariant have the same definitions. The third invariant is the determinant, and the second invariant will essentially be the sum of the principal minus. Okay. So let's go ahead with the next part. So far we have been discussing only about stresses. We know what it means to say stress components, deviatoric hydrostatic stresses, how to find principal values, what is meant by invariance of a stress tensor, all these things we have some idea. Okay. Now we talk about strains. Stress is independent of the material for a given loading, is just force by area. Okay. Strains is nothing but change in length by original length, also associated with the change with geometrical changes. There is nowhere you talk about Young's modulus when you are just talking about pure strain, right? So, however, when you want to relate the amount of strain induced by a certain amount of stress, you have to relate it through the material property. Okay, this function is unique for a material. So that is where your Young's modulus basically comes in. Okay, so we need to know Poisson's ratio, which I am sure you understand what it means. You also know what it means to say volumetric strains, change in volume by original volume. So with that, let's go to isotropic Hooke's law in 3D. This is a very essential aspect. So whenever your material is isotropic, isotropic means it does not have differences in the manner it responds to deformation or loading in different directions. A cube, a copper, FCC copper, face-centered copper is not isotropic. It has cubic symmetry. When you pull it in the diagonals, it will strain by a different amount as opposed to when you pull it along the faces. Okay. So the ideal isotropic material are amorphous material which have no underlying structure associated with them. It's very important. So in all our calculations, whenever we are doing a tensile test of copper or all those things, we still use isotropic Hooke's law. So I'll let you find out the answer for that as to why we are doing that. But the essential relationship that connects strains and stresses, as long as the material is isotropic, is given in equations 14, 15, 16 and 17. Okay. So sigma xx, sigma yy, sigma zz or zz are the normal stresses, whereas the epsilon are the normal strains, and then you have the gamma which are the shear strains, and sigma xy, I have written sigma xy instead of tau xy, but it's quite obvious, are the shear stresses. G is nothing but the shear modulus, which for an isotropic material is related to the Young's modulus, right? So these expressions and what I just mentioned as far as this slide is concerned, you all will be aware of from your fundamental strength of materials point of view. Now when you have small amount of thermal strains, you will have thermal strains in some of your real machine design problems. Under such conditions, the total strain is divided into two parts. One is the elastic strain, which is just caused by the stresses, and additional thermal strain, which is given by alpha delta T. So mostly although these equations are useful to know, we might not come across them as far as this QEEE program is concerned. So let us not worry about it at this point. Okay. So the basic things that we are going into the realm of failure theories. We are going to start talking about different types of failure and how we can quantify the failure of a particular material. So all the failure theories generally do the following. They say that whenever a certain function of the principal stresses reach some critical value, very sorry, whenever a function of the three failure stresses reach a certain critical value, then the material is said to have failed. Okay. We consider a continuum system. That means we don't care about the atoms and all those things that are actually there in the material. Okay. Then we talk about isotropic material, which is also an idealization, but is very good for practical purposes because the practical stress strain, all these things that you are doing on a piece on copper or steel or whatever it is, they are all isotropic. Okay, you need to think as to why that is the case. 4, we don't look at post yielding behavior. That means, so a material is there, we are deforming it, and it undergoes some permanent deformation, of course, or it fails. But if it undergoes permanent deformation, even after that you can continue loading it. Okay, different things will start happening. It will become hard, and all those things will start happening. We are not going to look into the post yielding behavior as far as ductile material is concerned. What I mean to say is, if you take a uniaxial, if you take a specimen and do a uniaxial tensile test on it, you might get a stress strain graph that looks like this. So somewhere here, it basically yields and it undergoes some permanent deformation. From beyond this, if you apply any small strain, the stresses are going to increase, and if you unload it, it will unload along this line parallel to the Young's modulus line here, this line, the linear point here, and this is called as the permanent strain or the plastic strain. We don't care in this course about what happens when we cross this spot. We are only going to be able to identify this spot, that's it. Once it has reached this spot, our material is failed. So for a ductile material, this will be the uniaxial stress strain response. For a brittle material, it's going to be something like, that's it, a straight line, and at this point it just fails. It doesn't show any plastic deformation. Of course, in general, for ductile material, it's much more stiffer, and you store very little elastic energy or strain energy, as you can imagine. But so yeah, what I wanted to mention is, we don't worry about what is going to happen to post yielding. That forms a part of plasticity, which is a different course. So now we come to discussing as to why we want to have only the deviatory component, and the reason for that is underlying mechanisms which cause the failure of the material. So first let's talk about ductile failure of the material. So what is a ductile material? So a ductile material is one which has a ductile material is one where the material can be drawn into threads, or it can be made flat into sheets and things like that. So this chalk piece can definitely not be, you cannot do that, right? You cannot draw this into thin wires. Whereas if you take a gold bar, it is possible for you to like flatten it out, deform it in such a way that it becomes a very thin wire, right? So gold is a very ductile material. Similarly, copper is a very ductile material. For ductile materials, if you draw the stress strain graph, like I just showed you, it looks something like this. There will be a significant, it differs from material to material. So those details are not important to us. It's important for you to understand that it can be stretched or deformed to a large extent without the material breaking. Okay, that is a ductile material. Now, why do ductile materials behave in a ductile manner? What is it that is causing them to flow? Like, flow basically when you apply some kind of loads. So the basic reason for this is, please show slide number 16 if you don't mind. So the basic reason for this is the development of the presence of dislocations in the material. Okay, a dislocation, as you can see on slide number 16, and there are different planes of atoms which are labeled A, B, C, D on slide number 16. Okay, this plane of atoms A is going halfway into the crystal, whereas the remaining half there is nothing. It doesn't continue into the crystal at all. So this extra plane of atoms that is present is causing some sort of distortion to the crystal lattice. So in the vicinity of that, near the region where the two planes basically come together like that, there will be some excessive stresses will be there, and that region, that particular defect, okay, that particular defect in the crystal is called as a dislocation. Okay, because the energies are high, when you actually apply a shear stress like what is shown in the second slide, this dislocation will slip. Okay, will just move like this caterpillar in a caterpillar wave-like motion and result in some sort of a permanent deformation with one unit cell protruding out. If you can see the slide number 16, it is going to be a little bit more clear. So this slip on application of the shear stress or loads is actually causing yielding or ductile behavior. So in FCC metals, there are so many different possible ways by which the dislocations present in them can slip, because of which FCC materials are extremely ductile. Aluminium, copper, gold, silver, all these things are very ductile. Now, if you take other materials, for example magnesium, which is hexagonal close packed, HCP, okay, it doesn't have so many possibilities for the slips to slip, for the dislocations to slip, because of which it is slightly more brittle when compared to the FCC materials. Magnesium is a brittle material. Okay, so the underlying microscopic differences which cause a material to be ductile or brittle is the presence of dislocations and the number of slip systems which are basically there in the material, allowing these slips to move around. Obviously, if there are more slip systems, the dislocations can keep happening in different directions and different ways, because of which you can draw these metals into thin wires and sheets. Whereas for other materials like chalkies, which don't have, this is not a good example to give because this is not necessarily a crystal, but imagine say magnesium, if you take magnesium, it will not, the dislocation will not be able to slip. Because of that, they will fail in a brittle manner. So a ductile manner, allowing the dislocation to slip forms a very important criteria to enable yield, or if we all agree upon the fact that yielding is actually failure, it is important for the material to fail, you need to make the dislocation to move. Okay. Now as you can see, suppose this dislocation, I am just representing the atoms as lines. This is that extra plane of atoms A that is there in slide number 16. Okay. Suppose I am taking this crystal structure and exposing it to hydrostatic stresses. Okay. I am exposing it to hydrostatic stresses. That means from all the three directions it is being equally stressed. Either it is being pulled or pushed equally. It will not cause this dislocation to move, isn't it? It will just stay there. You need some sort of imbalance for the dislocation to move. So for that you need this deviator, the one that changes shape, not that changes volume, to actually cause these dislocations to move along this particular plane, or the slip plane as they call it. Because of this, as far as ductile material is concerned, the deviatory component of the stress tensor becomes very important. Okay, it is that which basically distorts and causes the dislocations to basically move. So we now come to the first failure theory, which is the distortion energy theory, which is actually based on this or associated with the dislocation motion nicely, and it tells you that it's called as a von Mises theory or the distortion energy criterion. It tells you that whenever the elastic strain energy density associated with distortion in the particular material at a given point reaches a certain critical value, the material yields or the material fails. So that is kind of told to you on slide number 17. So whenever distortion strain energy density, strain energy per unit volume under a given load reaches a certain critical value, the material yields. The critical value is the distortion strain energy density at yielding during a uniaxial tensile test. We will come to that a little bit. Okay. So what I wanted to say here is also that the hydrostatic stress play no role in moving the dislocation. Only sigma d or the deviatory component, which causes a change in shape or something like that, causes this dislocation to move. So that brings us to von Mises theory, and I have given the statement there. It's a very, very important theory for ductile materials. Okay. So so we need to find out what this material is. So first thing is we need to calculate the strain energy density that is associated with distortion alone. So what do we have to do? We have to find out the total strain energy density U, the strain energy density that is associated with the hydrostatic stress, the hydrostatic component of the stresses, and then subtract the two, U minus UH will give you the distortion strain energy density. So until this, okay, this is what this is the exercise that we are going to do now. So what is U? U is half sigma 1 sigma I epsilon I. So what I am going to do is, okay, let me not do that. Okay, let me just do this. So sigma 1 epsilon 1 plus half sigma 2 epsilon 2 plus half sigma 3 epsilon 3. Remember that Actually, the state of stress at a point will contain 6 components, all xy, tau xy, all these things will come, but those things are not necessary. If we are able to find out the principal coordinate system, it is enough and equal to working with, it is enough and sufficient for us to just look at the principal components alone without any loss of generality or information. Okay, so here sigma 1 is the principal stresses and epsilon 1 are the corresponding strains. Okay, now we can relate strain to stress using this expression. Similarly for the other two, and plug them over here, and this will basically give us an expression for the total strain energy density to be what is there on equation number 23 on slide number 18. So 1 divided by 2E, so you get sigma 1 square plus sigma 2 square 3 square minus 2 nu sigma 1 sigma 2 . This is the expression for the total strain energy density. This is energy density. Stress times strain. Strain has no units. Stress has units of Newton per meter square or joules per meter cube. So energy per unit volume. Okay. So strain energy density at a given point with some stress tensor can be written down in terms of the principal stresses. Now if you want to find out, we want to find out the hydrostatic component of this. So what do we do? It's very simple. What do we do is we just replace sigma 1, sigma 2, sigma 3 by hydrostatic stress. So let sigma h be the hydrostatic stress, you get this. So sigma h square, so 3 sigma h square. So you will get 1 divided by 2E. So 3 sigma h square minus 2 mu into sigma h square. So you will get sigma h square divided by 2E into 3. So this will be a 3 here and this is going to be 6. So 1 minus 2 nu. So what is sigma h? Sigma h is sigma 1 plus sigma 2 plus sigma 3 by 3. So this will reduce to, I don't know whether I should write here because I don't know whether you can see. So I will write it here. You'll get there will be a 9 here because sigma h is sigma 1 plus sigma 2 plus sigma 3 by 3. So square of it there will be a 9 here, and this one is obviously sigma 1 square plus sigma 2 square plus sigma 3 square plus 2 sigma 1 sigma 2 plus 2 sigma 2 sigma 3 plus 2 sigma 3 sigma 1. Okay. So this expression, 3 to 6E. So 6. This expression is the expression for the hydrostatic component of stress. So that will be there in equation number I think 29, right? Yeah, 29. I think there is 1 2 missing there for sigma 1 sigma 3, so that's a typo. So it should be there over here. Okay. So 1 minus 2 nu by 6 E. There's no minus sign. Now you want to subtract this and this. So I'm going to do that. I'm going to erase this and do it because you have the final expression for sigma h over there. So U distortion will be equal to this minus this, and what will that be? That will be, so you have square 1 by 2A minus So sigma 1 plus square, sigma 2 square, sigma 3 square has been removed. 1 by 2e minus 1 minus 2 nu by 6e, then plus this part. So let me remove the minus sign here. So you have sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1 multiplied by, you have 2 nu divided by 2e. Okay, minus sign is removed. 2 nu divided by 2e. Since there is a minus sign removed here, we have plus 1 minus 2, so 1 minus 2 nu divided by 3e, because this 2 and this 6 will cancel and you will get a 3 here, right? Is that right? Okay, looks okay. Let's see what we get. So when we perform this operation, what do we get here? So here it becomes, this one will reduce to 3 minus 1, 2 plus 2 mu, 2 plus 2 mu divided by 6e, this term. So this term will become, so 3 minus 2, 1 plus nu divided by 3e, so which is also this, right? This is also the same thing. So 1 plus nu divided by 3e. So I've just written this part and this part. So this gives us the final expression for the distortion energy, which takes the following form. So you have 1 plus nu divided by 3e times sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. This is the energy stored at a particular point only because of distortion energy. Okay, distortion strain energy density is given by this expression, which should be there in, okay, this is also written in the form of equation 31. Okay, this is also equation 31. You can try it out, but this is basically the same expression here. So I'll just give you a little bit of a minute to take a look at that before we proceed. So what have we found? We have found, why are we doing all this? We said that, von Mises criterion is one where it says that whenever the distortion strain energy density reaches a critical value, it fails. Okay, so we are finding out the distortion strain energy density. The expression for distortion strain energy density is this value which I just wrote down. So expression for the distortion strain energy density is, I'm going to write down the one in the slide so that you can follow from here in case you just missed the derivation. This is the strain energy density stored in the material. So a material is arbitrarily loaded, right? At every point you can calculate this number. At every point in the domain you can calculate this number. Now how will you know whether that particular point is failing or not? You need some right hand side, right? You need to say that the distortion strain energy density stored at that particular point was equal to some number because of which I claim that particular point has failed. Correct? So how will you find out that right hand side? So that's what I am going to talk about. What you do is, you take that material and perform a uniaxial tensile test. You will get a stress strain graph like this. Uniaxial tensile test. So this number is called as the yield strength of the material. Yield strength of the material. Now, for that material, for this material, you have only performed a uniaxial tensile test, right? You have just pulled it like this, and it yielded, it failed at a value of sigma 1 equal to sigma y. So this is my 1, this is my 2, and then this is my 3, pointing outside the board. Okay, when the value of sigma 1 was equal to sigma y, it failed. So what should be the critical value? To find the critical value, I can find the distortion strain energy density at yield for that material. I perform an experiment, I just need one number sigma y and plug it in here, 1 plus nu divided by 3, sigma 1 was sigma y, sigma 2 was 0, sigma 3 was also 0, and this became sigma y square. So this is a number, the clear number, you know what this number is. Here everything is unknown, you don't know, this is all a function of geometry and loading, right? It's all a function of geometry and loading. Of course, if you know the geometry, if you know the loading, you will find these numbers, but what I am trying to say is, you don't know whether this particular point is failed or not. Okay, to find out whether this particular point is failed or not, you equate this to this. This is a number obtained from experiments for the same material that you have, that is subject to arbitrary loading. So when you equate this and this, you get an expression which says whenever sigma 1 minus sigma 2 the whole square plus sigma 3 minus sigma 1 the whole square plus sigma 1 minus sigma 3 the whole square divided by 2 becomes equal to sigma y square, because this and this essentially cancel out, becomes equal to sigma y square, then the material fails. So what you will do, you will take this body subject to arbitrary loading at every point. Usually you don't have to do at every point, you have some idea where the stresses are going to be highest. So in those points you calculate this quantity, okay, calculate this quantity and check whether it is greater than or less than sigma y the whole square. If it is greater than sigma y the whole square, that means it is already yielded. Okay, we have to do different things now, we will not worry about it. We want to make sure, now all these values sigma 1, sigma 2, sigma 3, what do they depend? They depend on the amount of load that you have supplied and on the geometry of the material. So this criterion will tell you the right combination of geometry and loading for which this can be made less than this so that the material does not yield. So this is the von Mises yield criterion and is shown more clearly in equation number 34. So this is a very important criterion for ductile materials. So please make note of it. I think it's about 10 minutes, so I don't know, shall I give some time for questions, right? So I'd like to give some time for questions. It's about 10 minutes. So if you have any questions, you can ask at this point on the material that we have dealt with in this class. Which theory is best suitable for ductile material, shear stress theory or von Mises theory? Generally, okay, the question is which theory is best suitable for ductile material, shear stress theory or von Mises theory? In general, people use von Mises theory for ductile materials. Information is okay. Next, so experimentally also people have found that for ductile materials, von Mises does a good job. It means it's closer to experiments. TUPJB is asking, information is not lost if the stresses are in the principal form. Please explain. Yeah, so the idea is very simple. So when you take the best example that I will give is the velocity example. Okay, that's very clear is very easy to understand. Suppose you have a coordinate system like this. Okay, and we have a vector v. This is a velocity vector. It has vx times I plus vy times j as the vector v. This is some arbitrary coordinate system. Because of it, it has a component in the x direction, it has a component in the y direction. Now imagine I keep rotating this reference frame, I keep rotating this frame of reference in such a way that the new x-axis actually coincides with this vector. Now what will be the component in the new x direction? It will only be vx prime times some I cap. There will be only one component for this vector, isn't it? Because in the other in the rotated frame, on the other component it has no component on the other for the y. Okay. Have you lost any information concerning v? You have not lost any information concerning V. V is still the same vector, it still has the same magnitude, right? In a similar spirit, you have a stress tensor which is written in some arbitrary coordinate reference frame. Okay, now I am rotating the coordinate reference frame in such a way that some of these components vanish, the shear stresses vanish, and I only am left with the principal stresses. So now I am in the principal coordinate system. Okay, when I am in the principal coordinate system, it is still the same physical tensor that I am working with. Therefore, I am not losing any information there. It is still the same physical quantity. What is the influence of deviatoric stress in a material? So deviatoric stress causes change in the shape of the material. They don't cause a change in the volume of the material. They don't keep the shape the same. Instead, they make a cube into a cuboid, they shear it and do all sorts of things. So only if the deviatoric stresses are acting on a particular material, the dislocations in that material will move. If it is purely a hydrostatic component, the dislocation will just stay there. That means it will not yield. Okay. So the Von-Mises theory is basically independent of the hydrostatic stresses and dependent only on the deviatoric stress or the deviatoric strain energy density rather. Resilience is the amount of strain energy stored per material in unit volume. Strain energy is the energy stored in the material within the elastic limit. A couple of questions. Can you repeat isotropic Hooke's law for thermal stress? Well, that particular equation there is correct, but it will take some time as to explain as to why that is the case. So let me not do that. Okay, let me not explain that. That is not needed for this session. So let's not talk about it. If you want more, maybe you can contact give the email address that was given to you by the QEEE people. I will explain there. Sir, if the dynamic load is much lower than the yield point, will it cause fatigue failure, or will the number of cycles increase? See, the dynamic, there are two, the question itself is a little confusing because talking about load, then you are talking about yield point, which I am assuming is stress. These two have different units fundamentally. Okay, it is true that the material under fatigue loading fails under much lower stresses than it does under static loading because the mechanisms are different, like what we will talk maybe in the next class. So yes, if that is what your question means, yes, the stresses can be at a much lower level if the stresses are oscillating, and the material will probably fail. So the maximum stress that the material is exposed to might only be half the yield strength. Nonetheless, the material will still fail. Sir, if the amplitude of dynamic load is much lower than the yield point, will it? I think I just answered that question. Rupesh Sahu, can you please? Yes.
Sir, can you please repeat the isotropic Hooke's law with thermal strain?
Okay, I will repeat it, but it is not needed. Okay, isotropic law in so without thermal strain, let me do it for one case. Okay, epsilon xx, the normal component of total strain is equal to right. This is the general Hooke's law when you don't have thermal strains. The total strain is equal to the elastic strain. This is called as the elastic strain. Okay. If you have thermal strains also, the total strain will be equal to the elastic strain plus the thermal strain, and this thermal strain is alpha delta T, right, if it's isotropic material. Similarly, you can write for all the three normal strains also. That is what is written there. Here I must, yeah, so that is what it is. Yeah, I don't know whether that is answered this question, but I think so. Okay, is that clear? Is that what you wanted? The total strain is always a sum of elastic strain and plastic or any other kind of strains like thermal strain or plastic strain and things like that. So for isotropic Hooke's law with thermal effects, this is how you need to write it. Total strain will be equal to elastic strain plus the thermal strain.
Hi, good afternoon, sir. Sir, I had that question about the dynamic loading. So like if the amplitude, so if the amplitude is like around half the yield point, so and like for steel we have that around after 10 million cycle it reaches a constant value which is around half the yield point.
Okay.
So if the load which we are applying, its amplitude itself is very less, like 0.1 of the yield point, then will the number of cycles is to like 100 millions to, or it won't affect it at all?
No, see, now you are getting into fatigue, which we have not discussed. So firstly, you are talking about something called as endurance limit. The endurance limit is the maximum amplitude of the stresses that you can apply so that the material never fails. Okay, so that the material never fails. Yes, so if the endurance limit for steel is like what you said, half sigma y, okay, and your maximum amplitude of stresses is only 0.1 sigma y, then theoretically it should come for infinite, it should never fail. However, what I am trying to tell you is that let's not talk about steel. At this point we don't know fatigue, so let's not talk about steel and endurance limit. I am only giving you a hint. I am only telling you that materials, when they are subjected to fatigue loading, when the load is actually fluctuating or varying with time, the amplitude of stresses that are induced which cause failure can be lower than what causes failure under a static case. That's all I am telling you. How many cycles depends on the amplitude.
Okay, thank you, sir.
Yeah, welcome. Sir, dynamic loading, according to which condition failure will take place? It depends on several factors. For complex stress cases, or when you have multi-axial fatigue, when all sorts of stress components are there, then we have to do some sort of approximation, like using von Mises and things like that to determine failure. But we still have to provide some background to address that question. So we will come to that in the next two classes. Why are we analyzing stress in the form of matrices instead of some other method? Because stress is a tensor. Because you have components because stress is not just associated with one number, like what you did in mechanics of materials. In order to be a little bit more general, we need all these 6 components at least. Actually 9 components, but we assume that the stress tensor is symmetric. So that is the reason why we are analyzing it in the form of matrices. I don't know any other method by which we can analyze it. Can we, I think, stop now? Thank you very much. It's 4 o'clock, so I'd like to